stretch or compress quadratics. And what we have done so far is we saw how to shift. We moved the graph right, left, up, and down. And then we also showed how to reflect the graph over the x-axis or over the y-axis. And there's one more transformation that we're going to do in Algebra 2, and this is the vertical stretch or compression. And the first exercise is going to illustrate what a vertical stretch is and what a vertical compression is. If we take a moment to look at this, it says, consider the quadratic function f of x equals x minus 2 quantity squared minus 9. And that's actually the picture that's already graphed for us on here. And it says, label the graph shown as f of x. So we're going to call that f of x. But on letter B now, what it says, on the grid, in a different color, create a graph of g of x that is vertically stretched 2 times that of f of x. Well, in order to make something vertically stretched, what we're going to do is we're going to multiply the y points, the y values of each point. In this case, because we're vertically stretching by 2 times, so this is going to be by 2. And what we've got on here is, again, we're looking at the y values of these points. So if we take our order pair here, the y value of this point is 0, and 0 times 2 is 0. So we're going to mark that one in. If we go to the y-intercept, which is 0, negative 5, the y value of that point is negative 5. And what we have to do is we have to multiply negative 5 times 2. And negative 5 times 2 is negative 10. Reading the graph from left to right, so the next point I'm looking at is 1, negative 8. And when we're vertically stretching, we're multiplying the y value of the graph by 2 in this particular case. The y value of this next point is negative 8. Negative 8 times 2 is negative 16. To negative 9 is our turning point, or our vertex of the graph. We're looking specifically at the y value of negative 9, and negative 9 times 2 is negative 18. Next point is 3, negative 8. Negative 8 is the y value, and negative 8 times 2 is negative 16. Notice I'm not changing the x value. Our next point is 4, negative 5. We're looking at the y value, negative 5 times 2, which is negative 10. And then the last point given on our graph here is 5, 0. And 0 times 2 is 0. And what we just did is we vertically stretched this graph. And again, how we did that is we multiplied every y value of the original graph by 2. Now, in a different color, if you so choose, we're going to create another graph. By the way, before I get going too far, I'm going to call my green graph the g of x. And what we're going to do next is we're going to vertically compress this graph. Now, we're going to compress the blue graph. So on the grid in a different color, create a graph of h of x that is vertically compressed by 1/2 that of f of x. Well, in order to do this, we're still going to take the y coordinates of the blue graph, of the original graph, and this time what we're going to do is we're going to multiply each point by 1/2. So it's the y value. We're getting, again, starting the graph at the very left, looking at the very left points. So our very left is this point here, negative 1, 0, and 0 times 1/2 is 0. The next point is our y-intercept, which is 0, -5, -5 times 1/2 is -2.5. So we'll graph at 0, 2.5, -2.5. The third point was 1, -8. We're looking specifically at the y value. -8 times 1/2 is -4. Going to our vertex is 2, -9. Half of -9 is 4.5. And it's -4.5. Our next point that we're looking at is 3, -8. Half of -8 is -4. Next point is 4, -5. Again, looking at the y value to compress this graph. And half of -5 is 2.5. And finally, our last point that we have been specifically given on this graph is 5, 0, and 0 times 1/2 is 0. And there is our picture, and I'm going to call a pinkish purple graph h of x. As we finish this question here, it says, what points did not vary when f was vertically dilated? Dilate means that we can make the graph bigger, or we can make the graph smaller. But what points did not vary when f was vertically dilated by factors of 2 and 1/2? And what happens is that the x values did not change because x's graph in a horizontal direction. I'm not sure I'm stating that very clearly, but it's better than what I have on my paper. They graph in a horizontal direction. X's, we go right and left to graph that value. And vertical is the up and down direction. So we're not going to change the x values because we're not going up and down. Now, if we flip over to our chart, we've got the last two to fill in. And here's what happens. And actually, I should fill it in on our regular notes before we fill it in on our chart. But if I go back here, it tells us what we need to fill in on our chart. It says the function h of x equals c times f of x represents a vertical stretch of the function if c is greater than 1. So for example, in our green graph, we had a vertical stretch of 2. 2 is greater than 1, so that makes it a stretch. And then when we're multiplying the entire function, so it's all going to be outside, when the number outside of the function is between 0 and 1, like the pinkish purple graph, we had a 1/2, so 1/2 is between 0 and 1, then we get a compression. But again, we'll go back and look at our chart here, and we can fill it in. Again, y equals c times f of x. If c is greater than 1, this is going to be a vertical stretch. vertical stretch. And if it's between 0 and 1, then it's going to be a vertical compression. Again, if you're used to this outside and this inside comments that I make, these are both going to be outside of the function. So if we flip our paper over, let's take a look here. And it says, how do I tell if the graph has had a vertical stretch or a compression? So the first thing is know the parent function and the pattern behind it. And we've been talking about that as we did the shifting right, left, up, down, and then the reflections. And you've heard me talk about some of these points already. 0, 0, 1, 1, 2, 4, 3, 9. One space to the right and one up. 2 spaces to the right and 4 up. 3 spaces to the right and 9 up. It could be 4 spaces to the right and 16 up. This is the pattern over here of the parent function that's given. And what we do to determine whether something has been vertically stretched or vertically compressed is typically we look at the vertex and then we look at the point that's 1 to the right and 1 to the left. Because notice, it's 1 to the right and 1 up, it's 1 to the left and 1 up. So if it's not 1 to the right and 1 up, and 1 to the left and 1 up, then something has changed. Occasionally, we can't tell from that first graph, or from that first point, then we have to look at the second point. But let's start here and see what we can figure out. And I put the parent function off to the side. You can see it above on your paper, but at least it's here so we can kind of look at it. Look at it, since this is the first time that we've seen vertical stretch and compression, at least for a while. And again, what the process is to determine whether, once we find the vertex, which is 0, 0, and then we look to the right, immediately to the right. Well, the point says 1, 3 on our graph. But if you look over here at the parent function, the parent function, 1 space to the right, is 1 up. And since the y value has changed from 1 to 3, what that means is that we have a vertical stretch. And what we did is we multiplied 1 times 3. So I usually write times 3, the x, for multiplication. A vertical stretch by a factor of 3. If we look at our next example, nice that at least we have the points in on this one, but the rest of them we don't. If we look closely here, vertex is still 0, 0, but when we go 1 space to the right, instead of going 1 up, we only go half up. So since that y value got smaller this time, this is considered a vertical compression. I usually write vertical compress. And again, it's 1 times 0.5. Well, that's going to be by a factor of 1/2 or 0.5 if you prefer to write it as 0.5. But in our third example here, we don't have any points put in here, but there's nothing saying that you can't go back and put in a point. As we take a close look here, we've got our 0, 0 here. And then if we go immediately to the right, we went 1 space to the right, but we went 1, 2, 3, 4 up. this is 1, 4. And what it looks like then is, from the parent function, normally we go 1 space to the right and 1 up, but we went 4 up. So this is going to be a vertical stretch. And it's 1 times 4 will give us the 4. So it's going to be by a factor of 4. Now what I said is, I said oftentimes you can look to the first point and go, oh yeah, I can tell what it is. On this particular graph, we can't see it right away. But we do have 0, 0. But we've got some portion of a point here on this first point. Over 1, up a partial value. And it doesn't even look like a half. And if we went over 2, we still can't see it's a partial value. Again, it doesn't even look like a half. So the next point that we can use is over 3. We went 3 spaces to the right, and we went 3 spaces up. We can tell that point right there. So if we look back at the parent function, what I have to do is I need to go 3 spaces to the right, because remember, the x values don't change. And 3 spaces to the right in our parent function is 3, 9. Now, one thing that we know here, and we're comparing the y values. So in the parent function, it was 9 for our third point to the right. Now our third point to the right is 3. Do we have a stretch or do we have a compression? Well, 3 is smaller than 9, so this is going to be a vertical compression. And then it's going to be by a factor of, well, 3 divided by 9, which is really 1/3. It's a vertical compression by a third. And I'm okay with 3 over 9. The 3 came from here, the 9 came from there. Again, most of the time we can look 1 space to the right and whatever, but in this particular case, we couldn't tell. So we have to go until we find a point that we can use. Number 5. We've got more transformations now. And as we take a close look, let's start with the vertex. In fact, let's identify the vertex. And what we see about the vertex here is that the vertex is 3, 4. So if we want to identify what's happening, originally we're starting at 0, 0, now we're at 3, 4. What that means is we went right 3. And we went up 4. Some of the other transformations we've talked about reflections. Well, it doesn't look like we had a reflection there. But again, in general, the pattern is we go from the vertex, from this point, we go 1 space to the right and 1 up. But we didn't go 1 space to the right and 1 up on this picture. We went 1 space to the right and 2 up. So we went from a distance of 1 up to 2 up, which means that this is going to be a vertical stretch. And it's going to be a vertical stretch by a factor of 2. We went from 1 to 2. 1 times 2 gives us 2. Number 6, start with the vertex again. Well, when we start with the vertex, our vertex is 0, -4. And what that tells us then for our picture is that we went down 4. We didn't go right, we didn't go left, but we did go down 4. This time our graph is turned upside down, so to speak, which means that we reflected, gotta spell it right, we reflected over the x-axis. We turned it upside down. The last kind of shift that we've been looking at today is, do we have a vertical stretcher? Do we have a vertical compression? And maybe we do and maybe we don't. Typically what we do is we go one space to the right and one up. Well, in this case, we're going to go one space to the right and one down because it's reflected over. But as we take a look here, this first point is a partial point. One space to the right and one down is what we're supposed to go. We're only going partial, so we can't really tell what this is. But we do know, since we are only going partial there, that it's going to be a vertical compress. And then the question is, how much? So let's go to the next point. And the next point, we went 2 spaces to the right and 2 down to get to that point right there. In the original picture, we went 2 spaces to the right and 4 up. So since it's reflected over, we should have gone 2 spaces to the right and 4 down. So what's going to happen is that we're vertically compressing by a factor of 2 over 4. Again, we went 2 down to get to this point here, and we should have been going 4 down from the parent function, which means that we are shrinking and we're compressing this graph by a factor of 1/2. Number 7. Again, start with the vertex. Well, our vertex is 0, 2. So over 0, up 2. So that means we went up 2. Doesn't look like we reflected, but it does look like we have some sort of vertical change. So we need to take that into account. And when we go 1 space to the right, we're going up a partial amount. We don't know how much. So we can't go 1 space to the right, 1 up. We can't compare that one. But 2 spaces to the right, we went 1 up. So now we can use this point, which I'm comparing back on the parent function to that point. 2 spaces to the right. Because we're not changing the x values, we're vertically changing. We're changing the y values. So as we finish up here today, what happens is it's going to be a vertical compression because we think we should have gone 4 and we only went 2. So we're going to vertically compress, and we're vertically compressing by 2 divided by 4, which is 1/2. So it's really by 1/2. Yep. I got that wrong. Sorry. It is vertical compression, but we went 2 spaces to the right and 1 up. So it's really by 1/4. Normally we go 2 spaces to the right and 4 up, but we went 2 spaces to the right and 1 up. So there we've got the vertical compress correct.